Thank you, everyone. And whoa, it's quite loud. I guess, ironically, I'm not going to be talking about F# today. Instead, I'm going to talk about Scala and Akka. So my name's Yan. I'm a principal engineer at a company called The Zone. And we are a subscription-based platform for you to watch live sports or watching sports on demand. You can think of us as Netflix, but for watching sports instead. And also, unfortunately, I'm not here to talk about what we do at The Zone because I applied the talk before I joined The Zone. So instead, I'm going to talk about what I did at my previous company, a game studio called Space Ape Games, where I was building backend for mobile games. So at Space Ape Games, we noticed that there's a trend happening in the last couple of years, whereby more and more of the top grossing games you find on the chart have got an element of real-time multiplayer. And we suspect that that trend is going to continue to grow because there's a number of enabling factors that have been happening, from better and faster networking and 4G being more available and also faster as well, and to everyone having more powerful devices nowadays. In fact, in 2017, the top grossing game in the whole world was not Overwatch, was not PUBG. In fact, it was a game made by Tencent and only available until recently in the West, called Kings of Glory. And this little-known game, well, that no one in the West knows about, has something like 80 million daily active users and a monthly revenue of $400 million. So obviously, the market opportunity is there. But when you try to build a game like this, essentially, you're trying to build a system whereby the client and server both need to send lots of small inputs, say 15 to 20 times per second, and you're very sensitive to any kind of lag. Anything beyond, say, 300 milliseconds in the round trip, you can definitely start to feel it. As you play the game, you start to move your character, and if you see a latency higher than, say, 300 milliseconds, you start to feel your character slow down. So that's not a very good user experience. And at the same time, you're trying to make these games and trying to make them run on mobile networks that are known for being unpredictable and oftentimes have limited bandwidth as well. And as engineers, that's a challenge to us. That is the technical challenge that we need to make these two things work together somehow. And along the way, we had to make all kinds of decisions, different trade-offs. Do we use some off-the-shelf solution to do this networking for us, or do we build our own? Do we use TCP, or do we use UDP? And do we want to have just all of our infrastructure in one region, or do we need to have a global presence? In terms of the trade-off and the constraint that we're working with, the most important thing we have to think about is the experience that we give to our users. And the most important factor in determining what user experience you give is the latency or the round-trip time, which we'll talk more about later on, what the user experience is. But at the same time, we still have to work within a reasonable degree of constraint in terms of the cost and complexity and how much overhead that we give ourselves from the operational side of things. So the first question we had to answer was, do we want to have a global presence in terms of infrastructure, or do we want everything out of one region or one continent? For most of the web or mobile applications, even when you have a global presence in terms of user base, you can still get away with having all of the infrastructure running out of one region. Typically, that would be in the US. And you can bridge the gap in terms of the user experience and latency with CDNs and edge locations that you get with cloud providers. And that works well enough for most applications, because even though you want your app to be fast, to be responsive, you don't have that strict requirement in terms of latency. Something up to, say, a 95th percentile of, say, 1 second is probably good enough for most people. But when you're talking about a mobile game where you're going to be sending lots and lots of small inputs very frequently and you're very sensitive lag, this approach is just not going to work. So like most people in this space, we decided that we have to have infrastructure all around the world so that we can be as close to our players as possible. So when I try to compare these two approaches, whereby I try to score them, and the higher the score, the better, obviously we need to think about the cost implication, the complexity, but most importantly, we need to optimize towards giving the best latency and the best user experience to our players as possible. So even though it means we have to run more infrastructure, therefore more cost, and we have to take on more complexity and operational overhead ourselves, in terms of the gain we get from the latency, this is the approach that is right for us in this particular case. And in this setup, we will have infrastructure all around the world, but our player doesn't have to be aware of that. So when they come into the game and they want to start a match, they will just get matched with other players in the same region without having to know about what regions we have set up in many of the desktop games you have played in the past, you may have to log on to the server, log into the game and decide what server you want to connect to. We don't want any of that complexity to be exposed to our players. They should be just log into the game, get routed to the closest server to them, and start playing a match right away. At the same time, having this global deployment and having this segregation of user base also has some impact on how we design our game as well. If you have a segregated user base, do you still want to have a global leaderboard showing everyone? And do you still want to have a group chat and alliances and those are kind of social features at a global level, or should they be regional now as well? And the next thing we have to think about is how is the client and server communication is going to work? We looked at a bunch of different approaches, and one of the more popular approach is whereby the server runs all the game logic. So the server runs all the simulations. The client sends the input to the server where the simulation happens. The server would act on the inputs from the players, update the game state, and then say 15 times per second, send out a delta to the game state to all the players. And on the client side, you just have to keep track of your current state, receive the delta from the server so that you stay in sync with what the server understands as the current state in the game. And whilst you wait for the server to respond to your input, you can start, you start moving your character, you can start doing some rendering using prediction to see where your character should be, and by the time the client, the server responds with the delta in the state, that's the moment you confirm that your prediction actually is right. And that allows you to hide some of the latency between the client and server so that you don't feel it when your latency is relatively good. And I think 300 milliseconds is the bar that we set ourselves. So suppose the server is sending out delta 15 times a second, and because we have to worry about latency, so when the client sends the input, the server may not even receive those input until, say, 2 frames later. And then only then the user's input actually gets acted on and affects the game state. And the delta of that game state is then sent out and received by the client a few frames later. So you're constantly having to deal with this synchronization issue on the client side as well as on the server side. And it happens so on and so forth for the whole match. And this is a very popular approach. Many games use this, Call of Duty, Vainglory, League of Legends, and Dota, and so on. I'm sure many of you are familiar with these kind of games. Most of these games are also played on a desktop or under Wi-Fi, where the networking is relatively good and stable. In terms of the advantages of this approach, you don't really have to worry about the client being out of sync with the server because you're always in sync so long that you're receiving the delta in sequence. And it's really hard to cheat because the game logic actually runs on a server, so it's hard for you to affect what a server is going to do. Only thing you can do is to send different input potentially. And if someone gets disconnected halfway through the match, reconnect is also really easy. Similarly, if someone joins a match halfway, then you can also just catch up by getting the current state of the game, and then from then on, only receive the delta. But the downside of this approach is that you're putting a lot of load on the server, and therefore you have to run more server to, say, host the same number of concurrent users. And because you're sending deltas in the game state, even if you're just sending the delta, that is still using a lot of bandwidth, which may be okay in the West, where bandwidth are normally quite good, even on 4G or 3G. But as soon as you go to the Southeast Asia, for example, the bandwidth is much more limited. So when I look at this approach, again, I try to score them on the different factors that I need to think about. In terms of cost, because you run more server and because you're using more bandwidth, and from talking to other peers in the industry, we know that at scale, your biggest cost is not going to be the server, it's going to be your use of bandwidth. And it's quite easy for you to be sending terabytes of data outside of AWS, and when you're sending data at that kind of level of scale, the cost can start to mount very quickly. And because you were sending quite a lot of data, it also means that it has a small impact on the latency your user experiences as well. So we looked at a few other approaches, and the one that we kind of decided on was what you call lockstep. But this is not the traditional sort of lockstep approach that many games you find in the sort of real-time strategy games would use, whereby it's really lockstep between multiple clients, where you're playing a red alert, for example, on the LAN, and you'll be connected to each other, and it's really a peer-to-peer connection whereby every frame, everybody confirms, what's our game state, what we've done, before you move on to the next step. So the lockstep approach that people do now on mobile is quite different. It's a small twist to that, whereby you send your input to the server instead, and the synchronization happens through the server. And the server will collect all the input from everybody, and then you broadcast only the input out, say 15 or 20 times a second. And on the client side, you are running all the game logic. So the server is not running game logic. The server is only telling everybody what everybody else's input is, so that you run a simulation on the client, and which means you need to make sure that all of your client in the same match is running the same version of a game engine, and everybody is receiving inputs in the same sequence, and when you run simulation, therefore everyone should also arrive at the same state. Again, you start to think about latency, and whilst you're waiting for the next input frame from the server, you use prediction to start rendering the behavior before you actually get confirmation from the server. And if you look at the interaction between the client and the server, it actually looks exactly the same as before. The only difference being that you're now getting the input from the server rather than actual game state. And we talked about the round trip time earlier, and how we measure it is the latency between the client and the server times by 2, plus the time at which point the server receives the input from the user in relative to where we are in the frame. So if the input was received at the start of the frame, server buffers them for, say, 60 milliseconds. If you're broadcasting 15 times a second, then that adds to the overall latency that the round trip time the user experiences. And that's the round trip time that we need to minimize and make sure that, say, 99.9999% of the packets are now falling under 300 milliseconds. So as you play a match, you don't experience any lag as you play. And this is an approach that's used by Kings of Glory for very good reason, because, again, this is a game that was very, very popular in Southeast Asia, where the network bandwidth is not very good, and also reduces the amount of load that you actually have to run on the server, and reduce the amount of bandwidth that you use. The downside is that you need to have a deterministic game engine, which should have been simple, except we use Unity 3D, and Unity has got a long-standing problem with deterministic floating point calculations. So literally, if you do 5 divided by 2, that code gets rendered to something different, different rounding depending on iOS versus Android. So 5 divided by 2 is going to give you different answers on different platforms, and now you're talking about you need to keep all the clients in the same match in sync, so they all reach the game state. That is a problem. So to get around that, we had to implement fixed point calculation, fixed point floating point, so fixed point maths ourselves, which is one of the complexities that we end up taking on as part of this work. And because all the game logic is running on a client, it also means now you're more vulnerable to hacking. And that means that eventually, at some point, you do still have to do validation on the server. You could do it per frame, so every time you receive an input, you check against what the server understands as the current state, or you can do it at the end when everyone has finished their simulation, and everyone says, if, say, 10 people are in a match, 9 of them says Team A won by 3-1, and one person says, no, Team B won, then you need someone to do the tie-breaking. And that's where the server can run a simulation all the way to the end, and then the result of the simulation from the server is the authoritative answer. And when someone gets disconnected, it's slightly more complicated than before, but you can still just ask the server for all the inputs since the last set of inputs that you have received, and after you receive that, then you can start to catch up, and then from then on, only receive new inputs from everybody. So compared to the server authoritative approach, we are taking on even more complexity because we have to implement the fixed point maps to get around the determinism problem on Unity 3D. But in terms of latency, we're sending less data, and having fewer server means that in terms of cost, this approach is much more feasible compared to running a server authoritative approach. And also, when you look at the coverage of 4G in China, it's not particularly great, and China is a massive market. And again, you need to consider the bandwidth that's available in China as well is all the way down number 74th in the world. And if you want to make your game a really big success globally, you have to design your system with those markets in mind and make sure that your game will actually work well when you go to, say, China, go to Philippines, and countries where the networking is not particularly good. So which brings us to the next question of, do we build our own stack, or do we use something like Photon, which is available if you're using Unity 3D? And we looked at Photon, we like it a lot, we use it for all of our development games and prototyping and so on, but there was a few things that really stopped us, and I don't want to be standing here and bad-mouthing Photon, because it is a really good product, but ultimately, in the end, we decided to build our own stack, and because the company is called the Space Ape Games, so we decided to call our stack Ape Sync. And we built it using Akka and Netty. So in terms of how the system works, it's logically very simple. You've got a match, you've got a current frame where you're collecting the inputs, and then you've got a history of all the frames that you collected so far. So when someone connects halfway or after they get disconnected, you can just send them all the history that they haven't received yet. And when someone connects to the server, they can get authenticated, and that records a new event in the current frame. And from then on, they can start sending input to the server, and every time they send something, that just gets buffered into the current frame. And then 15 times a second, we're going to go and broadcast all the inputs that we collected, including events for someone leaving, someone joining, to everybody that's in the current match. And then once we've done that, we will record the frame into the history, and from then on, we will start collecting inputs for the next frame, and so on and so forth. So logically, this is a very, very simple system. What makes complicated is the amount of concurrency that's happening on a server. You can quite easily have a few thousand people all playing against the same server, and every time as you try to broadcast, your users or your players also try to send inputs in as well. And it's not just one player, it's everybody in the same match all trying to send stuff to you whilst you're trying to broadcast stuff to them. And this is happening every single match all over the server. And that's what makes this kind of system complicated. It's not what we actually are doing inside. It's not a business logic. So instead, if you put a mailbox, instead of everybody updating the state in the match directly, you put a mailbox in front of everything so that whenever someone wants to send some input, they just politely send a message a letter to our mailbox. And we have an active system to then process those messages one at a time. And whenever we want to broadcast things to the players, again, we don't send to the socket directly. It goes through this letterbox, this mailbox we have in front of us, the sockets. And those are the actors we have in our system. One looks after the state for the match, one looks after the state for the player. And for anyone who's a big fan of Eric Evans's DDD book, this is what you call your root aggregates, where between them, everything happens through asynchronous message passing. So even when you have all these concurrent things happening at the same time, when you're working on the code, the nice thing about this approach is that you can just focus on what happens inside that match. What's my current state? What message have I just received? And what should I do given the current state and the message I have received so far, well, right now? You don't have to worry about everything else that's happening concurrently on a server. You don't have to worry about using mutex and other concurrency control mechanisms to make sure the state is being updated in a stress-safe way. You still have to think about how the different actors interact, but that's what you do at a sort of application protocol level. What I like about Akka and the actor model is that it allows me to solve otherwise complex problems very easily. And one of the things I learned from this project is that the trick to building something that's really, really performant is not to make something complex. It's actually simplicity itself. What is simple is much easier to optimize than what is already complex. In fact, what's already complex, chances are you're just going to, by trying to optimize it even more, you're just going to break it. And for this particular system we're talking about, performance is really, really important, because the more concurrent players we can host on the same server means fewer servers that we have to run, which means lower cost, but also it means there's less operational overhead for us as a team as well. And you might say, why do you have a picture of a Donald Knuth on the slide that says that performance matters? Isn't he the guy that's famously said that premature optimization is the root of all evil? Well, he is, except he's been misquoted all this time, because that's not all he said. The whole quote actually says that we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass up our opportunities in that critical 3%. So Donald is not saying, hey guys, don't do any optimization. He's saying, no, don't try to optimize before you know where is your critical 3%. So the next time you go to a meetup or an event or a conference somewhere and you see a speaker just showing you the first part of that quote, do me a favor, just quote them out, because that's not what Donald is saying at all. You'll be amazed how many times I sit in the audience and look at someone and says, oh, Donald Knuth says premature optimization is the root of all evil, so therefore we should not optimize at all. So in terms of optimization, we think actor model is a really good fit in the system we're trying to build, because threads are very, very expensive. They are OS level constructs, and every time you spawn a new thread, you allocate 1 meg of memories right away. And if you're talking about a 32-bit system, then in fact you're going to hit a memory limit that you can only have something like 1,500 threads before you get out of memory exception. And at scale, when you have so many threads all running at the same time, it's very likely for you to spend more CPU time on context switching than actually doing useful work. And actors being, actually I forgot to ask, how many people are not familiar with actors? Okay, a few hands, that's all right. So actors is a way to describe computation whereby, like in object-oriented programming, where everything is an object, in the sort of the actor model, everything is an actor, and the actor has got a mailbox. And the only way for you to communicate, to get something from the actor or to ask the actor to do something, is to send it a message asynchronously. And inside the actor itself, once it receives the letter from the mailbox, everything is single-threaded. So you process the messages one at a time. So inside the body of the actor, even you're maintaining some state that's being updated concurrently by multiple people, you don't have to worry about using logs and mutex and really heavy constructs like that to make sure that you are thread safe. And also because you're using actors, which is a high-level abstract concept compared to threads, you allow the actor system itself to optimize how many threads to actually run in order to minimize the amount of context switching you're doing, but still maximize the amount of work the amount of CPU time you can use. And we also use Netty, which is very performant, the non-blocking I/O library for JVM, and this makes it very easy for you to write TCP and UDP servers. Even though the UDP support is not very good, by default you can't really use all the cores you have on the server, so you have to do a bit of actual work yourself. And we looked at how we want to implement the application level protocols, what the server sends to the client. We look at different protocols. We looked at the protocol buffer, which we use quite heavily for RPC already. But even with protocol buffer, you're sending lots of small extra bytes for the tags between the fields. And we really want to minimize the amount of bandwidth we've used. So we ended up designing our own networking protocol between the client and server. So when the server when the client and server communicates, it happens via a custom protocol that's essentially all these bits packed really tightly together into a byte array. So debugging is quite difficult, but it does really minimize the amount of bandwidth we use. When I did quite a bit of network sniffing to look at what other games are sending in terms of bandwidth use, our game is easily about 1/10 compared to some of the games you play on some of the games I showed you earlier. And we also did a lot of work to make sure that we minimize the number of objects we create at both the networking layer as well as the application layer to reduce the amount of pressure we put onto the garbage collector. And we also find that with Akka, when you have actors that are just there for passing messages around, it does increase your latency, at least your variance in the latency. So we also reduce the number of hops that you have to do before a message goes from between the client to the match and back. We also make sure that everything we're allocating is buffer pooled, and instead of using the heap, we also use the direct memory as well. So we have for example, all the states for the match, or the different frames, or the different inputs, they get allocated to main memory outside of the heap, so that again reduce the amount of pressure we put onto the garbage collector. because if it's outside the heap, it's outside the responsibility for the garbage collector, and therefore you don't have to worry about the garbage collector having to clean those up later. But it does mean that you need to make sure when your match finishes, you also deallocate those direct buffers. Otherwise, you're going to run out of memory. Luckily, with the Akka framework, you have lifetime hooks so that you know when the actor has been created, when it has been closed, so that you can hook up to those events and make sure that you deterministically deallocate any direct buffers that you have allocated already. We also, at the sort of networking layer, we also have to disable Nagel's algorithm, which by default packages up small packets that you're trying to send over TCP so that you don't send so many small packets, you send one big packet instead. But in our case, that's going to impact the latency that we experience. You're going to add more jitter. So we had to disable that, which does mean that we are a bit of a bad network citizen on the network. But unfortunately, for our game to work, we kind of have to do it. And we also experimented with different TCP settings. We experimented with BBR, which from a lot of things that we've read and learned from others, we expected to see some improvement at the 95th percentile onwards. Interestingly, it didn't work out that way. In fact, when we enabled BBR, we saw everything below 95 percentile was a lot better, but from 95 percentile onwards, things actually got a bit worse. We never figured out why that is, but we didn't end up using BBR instead. And we do also use EPO, and interestingly, in terms of network optimization, the biggest gain we got was just to use the new ENA-enabled EC2 instances from Amazon. So if you're on AWS and you're using C5 instances, then you get ENA-enabled instances. You get ENA by default. Basically, Amazon redone the whole sort of networking stack so that when you're making those networking calls, it doesn't go through the virtualization layer anymore. It goes straight to the hardware, the hardware layer. So on those instances, you get much better, much lower jitter on your network API calls. By doing that alone, we were able to improve latency by about 20%, and without making a single line of code change, and the servers themselves were cheaper compared to previous generations as well. So, high five to AWS for making that happen for us. And we also implemented, interestingly, reliable UDP protocol ourselves. So when we put the game out into Netherlands and to Philippines as well as an early alpha to test the game as well as to test the networking capabilities, we found that in Netherlands, where the networking is pretty good, 4G and 3G coverage is very good and very stable, TCP was very, very good. It was as good as UDP. But then when you go to Philippines, where the networking is less stable, the bandwidth are much more restricted, we found that the number of TCP disconnects is so high that almost everybody that played the game, during one match, you'll be disconnected and reconnected a few times. And that creates lag, and that creates something that you can actually notice as you play the match, something is just stopped and then get reconnected and continue on. So to make our game more playable in those countries where the networking is not so good, we decided to take on the extra complexity of implementing UDP, and we decided to implement our own custom reliable UDP protocol, which means you're kind of repeating some of the things you get from TCP for free, but you have more control around how and when you disconnect players. And we were able to significantly reduce the number of disconnects that you experience as you play a match. And to make sure that we can improve our performance of our system and build a mastery, we also did a lot of work to automate our load testing. And one of the pain points I experienced in the past with load testing is how do you update the server? How do you have to wait 10 minutes for each 2 instances to be up and ready to run your load test. So instead, what we did was we wrote our client libraries, again, as Akka applications, and then we ran them inside Lambda functions, which you can spin up 10 instances of them very, very quickly in no time. I'm not going to go through what we actually did, but there's a blog post you can read about, and I'll make the slides available afterwards so that you can find the link as well. And we just make sure that we have a Jenkins build configuration that we can go in, click a button, and that will run a load test automatically, where the client or the Lambda functions would be talking to the game servers in different regions to simulate some delay in terms of networking. And we really, really optimize and focus on our efforts on optimizing the 99.99 percentile numbers to make sure that those numbers are well below the 300 millisecond latency that we know is when you start to feel the lag in the game. And to make sure that we can do all of that and so you know that our system is performing as we expect, we also have a lot of monitoring, and fortunately, you get a lot of that out of the box with Common, which gives you all kinds of metrics, including all the internal metrics from Akka as well, which is really useful. And just to final few slides. So when we, again, did a second alpha in Philippines and then in Netherlands, in Philippines, you can see compared to Photon, we have more high percentage of packets under the 300 millisecond benchmark, and we also about 50 milliseconds better at the 95 percentile and beyond. And in terms of the number of disconnects you experience as well, again, this is in a country where networking is really, really poor. We were able to significantly cut down on the number of disconnects compared to our own TCP implementation, as well as Photon's the reliable UDP implementation. So even though it did take a lot of work, we were able to improve our KPIs such as day one retention and session time across the board. And based on our projection before I left the company, our stack would be 14% cheaper compared to Photon. And with that, I'm out of time. And thank you guys very much for your attention. If you have any
Thank you, Yan.
Thank you.
I heard that you will be around for some questions and to discuss maybe, because we won't have time for Q&A right now.
Yes. So I'm going to be around the conference. I'm probably going to hang out outside for a bit. So if you're going to ask anything about the zone or Akka or building mobile games, feel free to come and grab me. Thank you.
Perfect. Thanks.